Hello everyone, this is Bahman, and today I'm going to be introducing to you all a machine learning library called TensorFlow. TensorFlow was open sourced by Google in 2015. This was developed and is used by Google to create their intelligent models for all their products. Therefore, it was designed to be made to work in a distributed fashion, so it can be run on multiple CPUs, GPUs, and even phones, essentially by running the same code. So what we're going to do today is that we're going to design a model that's able to recognize handwritten digits. So before we begin, I sort of want to go over some of the prerequisites that I think are necessary to be able to successfully follow this tutorial and fully understand what I'm going to talk about. So the first thing that I think is necessary is to have some knowledge of primary or basic machine learning tasks. So if you know what supervised learning is, then I think you should be good to go. Secondly, you should definitely have some understanding of basic linear algebra principles. So matrix multiplication, weighted sums, linear combinations. If you've taken a basic linear algebra course, then you should definitely be good to go. Third, I think proficiency in Python programming is very important. Without that, you're gonna not be able to follow along with the code, read it, or even get to write it. So the data set that we're going to be using today to train our model is called MNIST. Now, MNIST is a pretty old, a 20-year-old computer vision data set of handwritten digits. So the dataset contains these handwritten digits, as you can see on the screen, and along with them, they contain labels telling us what each image is. So for example, this 4 is accompanied by a label telling us that it's a 4, and I think there are around 60,000 images or training or data samples in this data set. So before we get into writing our model, what I want to do is I want to sort of explain and explore our data set. So here I'm importing the libraries I'm going to need, and here I'm reading the data set. And once we're done with some of those logistics, what we're going to do is get a batch from the data set. So I'm bringing in 13 images in the form X and Y, where Y represents the labels that describe to us what each image is, and X are going to be the images. So looking at the shape of X, we're able to see that it has 13 rows and 784 columns. So that essentially tells us that we have brought in 13 images, and for each of those image, we have 784 elements in the column. So what is the 784? What the 784 is that it's the flattened out pixels of the image. Now each image is a 28 by 28 pixel image, so we flatten that out and it gives us 784. So 28 times 28 is 784, and that actually allows us to use the data in our computations a little more effectively. So looking at the Y here, the Y in this situation, of course, we're going to have 13 because of the 13 images, and 10 because we have 10 classes that we're going to be classifying our data into. So for example, if there's a 0 here, it's going to be classified into one of the classes out of 0 to 9. So obviously that's going to be a 0, and 0 to 9 gives us 10 classes that we're going to be classifying our data into. Now, what do these labels look like? Well, looking at these labels here, they're actually in a one-hot encoded fashion. So as you can see here at one of these labels, one of the elements in this vector is hot, and the rest are all zeros. That tells us that the image described to us by this label is going to be a 6. So if we look at the image at the index 3 here, right here, if we plot it, we can see that it is actually a 6. So looking at the indices here, we go 0, 1, 2, 3, 4, 5, and 6. So that tells us that the image at x in x at the index 3 is going to be a 6, and that's how the label defines it to us. So we can use these images and these labels to train a model so that the model is able to predict new images that we give to it and classify those effectively. You can think about this as training a child on how to understand the number system. So imagine giving a child and telling a child, like, oh, this is 0, this is a 1, 2, 3, etc., and effectively hoping that the child will be able to classify new digits that you give it and understand that what each image is. So in essence, we're teaching a model the same way that we would teach a child how to understand the number systems and classify each digit into its correct class. So now that we understand how the data is organized and how it looks, we can go ahead and look at some of the math behind it. Here we have a linear function. So what we're going to do here is we're going to take our image, that big giant matrix, and we're going to apply the linear function to our image. Now, the x here is of course going to be the image. Now w and b are these parameters that we're going to be tweaking around and tuning to make sure our model fits the data correctly. So the w is the weight and the b are going to be the biases. These are the parameters we're going to be tuning to make sure this function fits our data very well, so we can predict new images. Now, once we apply the linear function to our images, to our features, what we're going to have to do then is we're going to be passing it into a softmax function. Now, this function, what it does is it creates a probability distribution from the output of the previous function here. What that's going to do is it's going to turn it into a probability distribution where each element within that vector will contain a probability or the likelihood of that image being that number. So if you can see here at the labels that we were looking at, think of it as turning into a probability distribution where the index with the highest probability would signal to us what the index would signal to us which class the image belongs to. So in this situation, if that one was a 0.73 and the rest were numbers lower than that, that would tell us that, okay, the index with the highest probability is what that image is. So it's a 6. So once we apply the softmax function to our scores from here, we can make predictions. But what we need to do is during training, what we're going to have to do is we're going to compare our prediction to the ground truth from the data set. And then we're going to calculate the distance between those two. And what we're going to do is we'll be using the cross entropy function to do that calculation for us. So this will calculate the distance between those two sets that we have, those two vectors, and then that essentially describes to us the loss of our prediction. And what we're gonna have to do is we'll have to minimize that loss by tweaking these two parameters, w and b, using something called gradient descent that we'll just look into. So that's the math behind it, and now we're gonna look at the code that I have here. Here I have so we need to describe some of the nodes or I suppose tensors we're going to be using in our code. So TensorFlow actually works in a very interesting way. It follows something called a deferred execution model. So the code that we write here is not actually going to run right away, or not going to be executed right away. What's going to happen is that it'll be TensorFlow will use this information here and create something called a computational graph. And once we have that graph, we can use a session to go and perform those operations described here. So we need to construct that graph first. Now, what we need to do is for our images, we need to make something called a placeholder, a TensorFlow placeholder. Now, the way that works is that TensorFlow has these little nodes in the computational graph, and that's essentially what each line here describes. Now, what a placeholder is a node whose values are going to be fed in during execution time. We obviously are not going to create a computation graph that depends on real values. We need to make a set of slots for them to put our data into. So what this essentially depends on is the type of data that we're going to be using, described here, and the shape of it. So these placeholders are going to be used to feed data into during training that we'll look into in a few moments. Now, the next thing here we're looking at are TensorFlow variables. Now, as I mentioned earlier, we're going to be tweaking the weights and biases, so we need to make these into variables. Now, variables are things we're going to tweak and tune to minimize our loss. Now, these are the two main things that we're going to be tweaking with our optimization. Therefore, they've been described as variables. To look at the shape of all three of these, we can see that for our x, the images, we have a none for the x. In the shape, we've written none. What that tells us is that we're able to put in as many images or training samples that we want to put it into. We don't want to constrict ourselves to a set number of images, so we've put none here, and 784, of course, because the number of pixels in the image. Here for the X, for the W, we have the 784, same thing, and 10 because we have 10 classes we want to classify into. And for B, essentially the same thing, 10. Now we've made them filled up with zeros because that's sort of the default value. This shouldn't matter what values are in there because the optimization algorithm is going to switch and tune them around into specific values. And they'll definitely be different from what they are now. Here we described our linear function. We describe our linear function as a matrix multiplication of the features and the weights. So it's just a big giant matrix multiplication. And then we add our biases to them. So that's the function that's essentially gonna make the predictions for us. Now, what we're doing here, we're making another placeholder. Now this is where we're going to put our labels into from our data set, the ground truths. So this is also going to be a placeholder because we're not going to be tuning it around. This is going to be a static data that we get from the data set, and it's also described as a none and 10 because of the classes. So now once we have shown our linear function and written it out here, we need to definitely apply the softmax function to it, and we need to use cross entropy to calculate the cost. So here what we do is we apply tf.nn softmax cross entropy with logits. So what that function will do for us, it'll apply softmax, the softmax function to our model here, or to our linear function. So here's the y underscore here, given as labels. That's our ground truths. The logits are going to be our predictions. And what this function will do, it'll take care of applying the softmax function, applying the cross entropy to calculate the cost, and return that to us as cross entropy here. Once we have that, we need to take that cost function and of course minimize the loss. Now the way we're going to do that is we'll be using something called the gradient descent optimizer. This optimizer here will take partial derivatives for the W and the B, the parameters, and take a step in the opposite direction of the gradient. What that will do is it'll actually take us to the minimum, I think the local minimum specifically, for a given function, and it'll be doing that with this learning rate that we've described as 0.5. Now, the learning rate is a number that if it's too small, it'll take too long for the minimization to happen, for the convergence towards the minimum. And if it's too large, we'll be stepping over our minimum, causing us to never actually converge or even diverge. So once we have described our optimizer object, we need to minimize a specific function, and of course that's going to be our cost function called cross entropy that we got earlier. This will take care of the entire process for us. It'll do the partial derivatives, the stepping towards the stepping in the opposite direction of the gradient, and all that's other necessary information it needs. So now here we've essentially described the computational graph in TensorFlow. So in order to execute the code and evaluate all these things, we need to start something called a session. So here I'm starting up an interactive session, and before we can work with any variables in TensorFlow, we need to initialize them using the global variables initializer. Now once we do that, we can take all these tensors and work with them in our training. What I'm doing for training is that I'm doing 1,000 iterations of training, and for each iteration I'm bringing in 128 images as a batch from our data set as our batch X's and batch Y's. Batch X's being the images and the Y's being the labels. And I'm running our cross entropy and our train step, which is our training function from the optimizer. I'm running them inside a session in this TensorFlow. So this will do all the evaluations for me, and here's where I'm going to be passing in or feeding in the data from my data set to replace those placeholders and put there. So this is where the data comes from, goes into the placeholders, and is run through the linear function through softmax, and the cost is calculated using cross entropy, and it is optimized using gradient descent. So this entire work is done in the background by TensorFlow, and TensorFlow knows what it needs to calculate each step. So here in train step, it knows that it needs to take care of cross entropy, so it sort of traverses backwards to take in the computational graph to evaluate whatever it needs to get the value for us. So that's the beauty of TensorFlow, where these tensors are flowing through the graph to do the computations. Now, what I'm doing here is I'm printing the loss for us so that we can see the changes in the loss per each iteration of the training, per each iteration of the training. So here I'm printing the loss given to us by cross entropy, and as we can see throughout the training, the loss decreases. So we started with 2.3 and we're all the way down to 0.21. Now this is where the training goes ahead and tweaks the weights and biases or parameters so that that function can fit the data very well, and we're able to make pretty good predictions, and the loss function allows us to see how well we're predicting, and we definitely are minimizing the loss here. Now once we got our function and we have minimized the loss, what we need to do is we need to test our model to see how well it's making predictions for us. So what we're doing here in this last cell here, we are going ahead and making our predictions. So here, once again, we're actually describing our computational graph. So what we're going to do here is to get the correct prediction, we need to compare our prediction with the ground truth. So prediction y, ground truth y underscore. And what we do for the accuracy is of course, we take the sum of all those predictions that we've made and then divide them by the number of predictions to give us the accuracy. Now, we run that within our session and we feed new data into it from mnist.test, not mnist.train. Now, here's why. We can't feed data into our testing. We can't feed the same data into our testing that we use for training, because that's sort of going to be like cheating. The model would have already seen that data, so the predictions that it makes would be ones that it already knows the answer to. So we use this new data from our test batch, and we test our model using that data to see how well the model performs given new data. So in this situation, we're getting to about 92% accuracy. So 92% of the time, the model was able to make the correct prediction and classify each digit into the right number. This may seem like a pretty good accuracy. However, we can push this up to 97, 98% if we were to make our model a little more complex. But for the reasons of demonstration and explaining TensorFlow, we've kept it pretty simple so that we can follow along easily. Now, I'll leave that to you to go and find out how to add a few more layers into your model so that you're able to push this accuracy higher. So I want to thank you all for your time, for following along with this tutorial for me. If you're interested in TensorFlow and looking forward to more tutorials, definitely check out tensorflow.org. You can follow the instructions how to install it and get started with it. Other than that, if you have any questions, please don't hesitate to ask me and I'll be sure to answer them. Thank you.